One last example before moving on. We have a large wrecking ball. It has a mass M. Notice in the picture their M is labeled. So that sphere is the wrecking ball. We know the mass. It's asking us for tension B in the cable that makes an angle of 40 degrees with the vertical. That 40 degrees is shown here. They do not give us tension A. So it's being held in place, meaning static equilibrium. Ultimately, meaning there's no acceleration in any direction. It's not moving, it's not going to move, it's being held in place. So our approach, as it has been all along, is to draw the free body diagram, write the forces that represent net force equals ma, or in this case, net force is 0 because there is no acceleration. This picture is nice. I'm going to go ahead and just draw my free body diagram on the picture. I know the force of gravity will point downwards with the force of mg. We know mass, we know g. We know this cable A is pulling to the left, and it's now already labeled. We'll keep it T sub A. We know this cable B is pulling along the length of the cable. Ropes and cables and strings can only pull, and they pull along the line of the rope or string. I'm going to draw my 40 degrees down here just so I can look at my x and y components. So B is going to have an x and a y component. There's nothing else in contact with this wrecking ball, and so our free body diagram is complete. In terms of writing our forces for the x and y directions. In the x direction, cable A pulls to the left, but that needs to be balanced by the x component of B's pull. Right? The wrecking ball is not moving, it's not going anywhere, so there's no acceleration. So the x-ward components need to equal each other. We could write tension B, the x component, as tension B, that side, this x side is opposite the angle. So tension A needs to equal tension B times the sine of 40. We don't know either tension A or tension B. That's okay. Let's go ahead and look in the y direction. The forces need to balance out in the y direction as well. That will keep the wrecking ball in place. We know tension B has an upward y component. Tension A does not. So the only upward force is the component of tension B. That needs to balance out the only downward force of mg. We can write this y component of tension B. It is adjacent to the 40 degrees in the picture. So the y component of tension B is tension B cosine 40. That needs to equal the mass times gravity, the acceleration of gravity. So this y equation will actually allow us to solve for tension B. 8 divided by. Now, please do not ever leave your answer like this. We have essentially 2 sig figs from the angle. So 2 sig figs, I'm going to write this in scientific notation. 2, 3, 4. 2 sig figs. The tension in cable B would be 5.2 times 10 to the 4th newtons. We could also write it as 52 kilonewtons, because this could be 52 times 10 to the 3 newtons. That would be fine as well. 52 kilonewtons is fine. But make sure we consider the significant figures, and it's always nice to not have to count decimal places when it's a really big number. Now that we have tension B, we could totally find tension A. Right? We just have to plug it in there. This problem didn't ask for that, but if it had, I would use the answer I got, not rounded, in terms of making this calculation. So 3.31234. Tension A, 3.3 10 to the 4th newtons, or 33 kilonewtons. Either of those would be fine.